All right, welcome. Today we are going to dive into a physics puzzle that's hiding in plain sight, everywhere from a simple credit card swipe to the huge generators that power our world. And it all boils down to this one really surprising question about energy and velocity.
I mean, it seems so basic, right? You just swipe a card and the transaction happens. But what's actually going on inside that little reader? You're basically performing a classic physics experiment every single time you buy a coffee.
You see, that magnetic strip on your card, that's the whole key. As you move it, that's the conductor, through the magnetic reader head, you are generating a tiny little electrical signal. It's this really cool dance between motion and magnetism.
And this whole phenomenon is described by a wonderfully simple formula for something called motional EMF, which is just a fancy way of saying voltage from motion. As you can see, the voltage, E, is just the product of the magnetic field, B, the length, L, and the velocity, V, you swipe the card at. Simple.
Okay, but here's where it gets really interesting and kinda weird. If the voltage depends on velocity, you'd think the power generated also just depends on velocity. And you'd be right, but it actually depends on velocity squared. So why? Where on earth does that extra V come from? That is the mystery we're solving today.
To really get the big picture of that moving rod, we have to zoom way, way down. I'm talking down to a single charged particle and see exactly how it dances when it enters a magnetic field. So when a charged particle flies into a magnetic field, it doesn't go straight. The field grabs it and forces it into a perfectly circular path. And the size of that circle, its radius, r, is determined by this formula. It all comes down to the particle's momentum, its mass times velocity, or its kinetic energy, k. And this analogy just makes it all click, doesn't it? A heavier particle or a faster one has more oomph, more inertia. It's just harder for the magnetic field to bend its path, so it ends up making a much wider circle. It's exactly like trying to turn a speeding truck versus, say, a bicycle. So, where does this formula even come from? Well, it's all about a perfect balance of forces. In step 1, you see the magnetic force, QVB, is the only thing pulling the particle sideways. So that force has to be the centripetal force, mv²/r, that keeps it moving in a circle. You just set them equal, and the rest is pretty much just algebra. Step 2, cancel a v from both sides. And then step 3, just shuffle things around to solve for the radius r. Okay, now listen up, because this is a classic exam trap. It is so easy to accidentally flip this fraction and write QB over mv.
So the crucial takeaway here is simple. More mass or more energy means a bigger turning radius. And this simple principle is used in everything from like old school tube TVs all the way to the giant particle accelerators at CERN. All right, so we know how one single charge behaves. Now let's zoom back out. What happens when you have a whole rod just filled with trillions of these charges and they're all moving together? Let's find out. Just like our credit card, when you move a metal rod through a magnetic field, you create a voltage across its ends. The rod literally becomes a temporary battery. And the formula for it? Well, we're right back where we started. E equals BLV. So how does this even happen? Well, that rod is jam-packed with charged particles, right? As the whole rod moves, every single one of those charges feels that same magnetic force we just talked about. But they're trapped inside the metal, so instead of flying off in a circle, they just get shoved to one end of the rod. And that separation of charge, well, that's the very definition of a voltage. Now, if you take that rod and connect it to a circuit, that voltage is going to drive a current. And that current is going to dissipate power, usually as heat. And the formula for that power is P equals V squared, L squared, V squared, all over the resistance R. And there it is, V squared.
You see that? This right here is what our sources call the CBSE gold trap. And for good reason. Apparently, a staggering 75% of students get this wrong on exams. They forget the square on the velocity. It is the single biggest mistake people make with this formula. Do not let that be you.
So let's burn this into our brains right now. Seriously, the best way to remember is to just repeat it. Say it out loud. V squared in the power formula. Power is proportional to velocity squared. That is the key. So we know what the formula is, but now it's time for the why. Why is it V squared? Well, the answer lies in one of the most fundamental laws in all of physics, the conservation of energy. Let's see how it all connects. You can't just create energy out of thin air, right? So the electrical power that's being generated has to come from somewhere. And it comes from the mechanical work you do by pushing the rod. This slide shows it perfectly. The mechanical power you put in is just force times velocity. The electrical power you get out is voltage squared over resistance. And when you plug in the formulas for force and voltage, look at that. They become the exact same expression. And there it is. That's the answer to our big question. The V squared shows up because power depends on two things: the force you have to apply and the velocity you're moving at. But in this case, the magnetic force that you have to push against also depends on velocity. So velocity gets counted twice, once for the force and once for the movement. That's where V squared comes from. Okay, so we've connected all the dots, from a single little particle all the way up to a full circuit. Now, let's switch gears and make sure you can use this stuff to absolutely ace those exam questions. Here's your game plan. For particle radius, just pick the right version of the formula based on what the question gives you, momentum or kinetic energy. For motional EMF, always check that the motion is perpendicular to the field. That's another common trap. And for power, my best advice is to write the V squared down the instant you write out the formula. Before you do anything else, just make it a habit.
And I'll leave you with this final thought to chew on. A magnetic force, by itself, actually does no work on a single charged particle, because the force is always perpendicular to its motion. So, how is it possible that moving a whole rod full of those particles through a magnetic field does generate usable energy? It's a subtle but really deep question that gets right to the heart of everything we've talked about today. Think about it.